Greetings, everybody. Learning is a hobby here. I know it's been a while since I've made a video. We're at the end of the semester, so you know how, I don't know if you're a teacher, you know how it is at the end of the semester. Finals week just started, so I got, I'm just really super busy, but I managed to get the summary for section 3.3 written up here. So I'm going to make the video for the summary for section 3.3 in Tau in this video. And hopefully I'll be able to get the solution set posted at some point next week. But again, it depends on how quickly I'm able to get all this the end of semester stuff wrapped up, which, like I said, it's quite a bit. So just bear with me. uh, I'm going to really make a push to get the exercise set out by next weekend. But anyway, that's neither here nor there. You want to hear about section 3.3, so we'll start on that in this video. Like I said, we're going to look at section 3.3 in analysis 1 by Terence Tao. This is the chapter on some basic set theory stuff, and section 3.3 is on functions. So let's bring up my notes here. All right. So in the last section, 3.2, we talked about Russell's paradox, and we talked about the axiom of foundation. And in section 3.1, we talked about the other axioms of set theory. Now we're going to look at functions, like I said. So we'll start with the definition, but before we do that, he says in the beginning of the chapter that in addition to the notion of a set, in order to do the mathematics that's required for analysis, we also need the notion of a function. So we'll start with the definition of functions. I probably should have numbered this definition. I don't know why I did. This is probably definition 3.3.1. He probably numbered it. Let me just double check. Yeah, 3.3.1. I probably should have. Let me just write that in here just so, because we're going to probably end up referring back and forth to the different definitions and everything. So let me just add the numbering system here. This is definition 3.3.1. Okay, so here's the definition that he uses in the book for a function. Let x and y be sets, and let p of x, y be a property pertaining to an object x in the set x, and an object y in the set y, such that for every x in x, there is exactly one y in y for which p of x, y is true. He says sometimes this is referred to as the vertical line test, which you probably are familiar with from, if you took pre-calculus or algebra at some point in your past. Then we define the function f from x to y, defined by p on the domain x and codomain y, to be the object which, given any input x and x, assigns an output which we call f of x in y, defined to be the unique object f of x and y for which p of x, f of x is true. Thus, in other words, for any x and x and y, y equals f of x if and only if p of x, y is true. All right, so that's the definition that we're going to use for a function. All right. Now he says in remark 3.3.2, he says something about that definition. So we'll talk about it here. It is implicitly assumed in the definition above that given any set x and y in the proposition p that satisfies the vertical line test, that one can always form a function f. Strictly speaking, this should be an axiom. The result of exercise 3.510 makes this redundant, since it's always possible to encode a function f as an ordered triple, where the ordered triple is x, y, comma, the set of all x, comma, f of x, where x is an x, consisting of the domain, codomain, and the graph of the function, which gives a way to build functions as objects using the operations provided by the previously established axioms of set theory. So, when we get to the exercise set, well, that's one of the exercise. Oh, I'm sorry, 3.510. That's actually in a later section. So when we get to section 3.5 in exercise question 10, we'll cover that. So actually that's going to be a few sections from now. But anyway, when we get there, we'll talk about this more in depth. Also, implicit in the above definition is the understanding that every function f is automatically associated with a domain x and a codomain y, and a defining property p. All right, so he gives an example here. A lot of the examples are, you should, if you've taken math courses before, this shouldn't be like new, particularly new to you. But anyway, he gives some examples here. Let x be the natural numbers, y the natural numbers, and p of xy be the property that y is the successor of x. This defines the increment function that we talked about in chapter 2, f from n to n, where f of x is the successor of x. We can define a decrement function, h, from the natural numbers -0, that's set difference, by the way, to n, the natural numbers, associated to the property p of xy, defined by y, y, how do I say this? Y plus plus equals x. So in other words, x is the successor of y. So in other words, y is the predecessor, I guess maybe you could call it, the predecessor of x. Since when x is an element of the natural numbers -0, there's exactly one y in n, such that x is the successor of y by lemma 2 to 10. Notice, however, that g from n to n, p of x, if and only if x is the x is the successor of y, does not produce. Sorry, just hard to say that. Maybe I could say what, like, y is the predecessor of x. Maybe that would be easier to say, but does not produce a function, since there is no y in n in the natural numbers where the successor of y is 0. Right? We chose that as an axiom in chapter 2, if you remember. All right, exercise 3.3, not exercise, example 3.3.4. He says informal here because we haven't formally defined what the set of real numbers are. We'll do that in a later chapter. But so for the moment, when we talk about exercises involving the integers or the rationals or the real numbers, he labels the examples informal because we haven't yet formally defined those sets. But anyway, the real numbers will be defined in chapter 5, so we will eventually define them. But for now, it's considered informal. If we try to define a square root function, f from the real numbers to the real numbers, by p of xy, if and only if y squared equals x. Sorry, this is not proper English the way I wrote this out. This, I don't need that however here. This would lead to two problems. Let me actually let's fix the English here. Let me just make this a little bit wider. Sorry, just bear with me for a second. I'll say this would lead to two problems. Okay, so the two problems I have listed here. So problem number 1, the square root of x is not a real number for some x in R. For example, if you take x equals -1, right? That's not, the square root of -1 is not a real number. And problem number 2, if x is in the positive real numbers, then there are two y's in R, such that y squared equals x. For example, if x is 4, then y1 is 2 and y2 is 2, and both satisfy the proposition y squared equals x. So to get around this, we restrict the domain and the range, or sorry, we haven't talked about ranges yet. We restrict the domain and the codomain x and y to be the non-negative real numbers. Then we can define a function f from the non-negative real numbers to the non-negative real numbers, where p of xy is the proposition y squared equals x, and p of xy will satisfy the vertical line test. This is an example of an implicit definition for a function. He talks about implicit versus explicit definitions, and then a little note that he has. So functions can be defined explicitly by specifying the domain, codomain, and the rule that links x to y. In other words, y equals f of x for some rule. Sometimes we simply state the rule and omit the domain and the codomain. For example, if you just say, if we have the function f from the natural numbers to the natural numbers, where f of x equals the successor of x, sometimes we just say f of x is the successor of x and just, don't write down explicitly what the domain and codomain are. You guys are familiar with this if you've taken math courses, right? With something that's pretty standard. Functions can also be defined implicitly by simply stating the property p of xy, linking x and y. An implicit definition, however, of a function is only valid if for each input x, we know there is exactly one value y that satisfies p of xy. For example, the way we defined the square root function in the previous example. All right, so you can define functions explicitly by stating the rule for getting y from x, or you can state the proposition that has to be satisfied between x and y um, under the condition that it be a function, right? It has to pass the vertical line test. Here's a proposition. Remember, just to remind you guys, when you see in my summaries of the chapter something like this without a number next to it, this is not something that Tao writes as an actual theorem or proposition in the book. It's part of the chapter where he's explaining something in a paragraph or something in English, and then he asks you why. So here he asks a question why, and I proved why it's true here on my own, which again, you should get into the practice of doing when you're reading math books. So here's something that he asks us to check. So functions obey the axiom of substitution. Right, here's my proof. Let f from x to y be a function satisfying p of xy, and let x prime be elements of the domain x, such that x equals x prime. Then p of x f of x and p x prime f of x prime are true by the way I defined the function. Furthermore, since x equals x prime, p of x f x prime is true. And since f is a function, that means that f of x has to equal f of x prime, and that shows that the notion of function is well defined. All right. Another note here: for functions, equal inputs lead to equal outputs, as shown in the above proposition. However, unequal inputs may not lead to unequal outputs. Again, you guys should be familiar with stuff like this, like the squaring function, or in the example that he has next, a constant function would have that property. So here, example 335, let x be the natural numbers, y be the natural numbers, and let p of xy be the property y equals 7. Then clearly f of x equals 7 is a function, but notice that f of 1 equals f of 2 here, they're both equal to 7. In fact, for any natural number, f of that natural number will be equal to 7. It's a constant function, for example. So you can have different outputs leading to the same, you can have different inputs leading to the same output, but not the reverse of that. All right, here's remark 336. We now have several different situations in which the use of parentheses are required. However, it should be clear from the context which usage is meant in specific instances. So he's just giving you, a heads up there. There's a lot of different notations that use parentheses. But again, there shouldn't be any issue about confusion if you take the context into account. Again, if you've taken math courses, I mean, this should be sort of like, you guys understand this, hopefully. But anyway, remark 337, we don't necessarily require functions to be sets, nor do we require sets to be functions. However, it is permissible to start with a function, f from x to y, and construct its graph, which is a set of ordered pairs, x f of x, where x is an x, which defines the function completely once x and y are specified. All right, next we have a definition. This is definition 338. Here we're going to define what it means for two functions to be equal to each other. Two functions, f from x to y, g from x prime to y prime, are said to be equal if their domains and codomains agree, meaning, x equals x prime and y equals y prime as sets, and furthermore, that f of x equals g of x for all x and x. if f of x and g of x agree for some values of x in the domain but not others, then we do not consider f and g to be equal. He has a little annotation here in the book, which is why I have the star in the superscript here. He says that in volume 2 of this of his analysis books, so this is volume 1 that we're doing. In volume 2, we will discuss a weaker form of equivalence that's called equivalence almost everywhere. We need measure theory to talk about that. What that means is equivalent on uh, they're only unequivalent. Is that proper English? They're only not equivalent to each other on a set of measure 0. But we haven't talked about measure theory. That's a more advanced topic that we'll do in volume 2. But anyway, if f and g have different domains or ranges, we also do not consider f and g equal. All right, so this is the condition for two functions to be equal to each other. And then he has a remark right after this. While functions with different domains or ranges are not equal, we will sometimes, quote, abuse notation by identifying such functions together if their values agree on their common domain of definition. Again, this is something that if you've taken, algebra or pre-calculus or calculus, I mean, you've probably, you've done this kind of thing. It's not convenient to always write things out as formal as possible, right? So here, example 3.3.10. Again, this is informal because we haven't defined the set of real numbers yet. The functions x from where x goes to x squared plus 2x plus 1 and x goes to x plus 1 squared are equal on the domain R, because they're functions from R to R, and for every x in R, f of x is equal to g of x, right? The functions x to x and x to the absolute value x are equal on the set of non-negative real numbers, but they are not equal on the set of real numbers. They disagree on the set of negative real numbers, right? For example, for the first function, if x is -1, then y is -1, whereas for the second function, if x is -1, y is +1. Okay, here's another example. The empty function f from the empty set to x is the function whose domain is the empty set. Now I said the function because he says here in a note after the example, for each set x, there is only one function from the empty set to x, and he asks us why, so I'm going to prove it here. Right, so let f from the empty set to x and g a function from the empty set to x. Then for any x in the empty set, f of x equals g of x trivially, since the empty set obviously has no elements by definition. Therefore, f equals g by definition 338. Okay, remark 3.3.12. It is not immediately apparent that definition 338 is compatible with the axioms of equality from appendix section 7. Appendix A, section 7. And we'll explore that in exercise 3.3.1. So when we get to the exercise, when I make the video on the exercise set for this section, that's the first problem that we'll look at. There are at least 3 ways to address this issue, possibly more, but he lists 3 different ways to address it here. Possibility 1, we could regard definition 338 as an axiom rather than a definition. Or option 2, provide a more explicit definition in which definition 338 becomes a theorem. For example, we could define a function f from x to y to be an ordered triple xyg consisting of a domain set x, codomain set y, and graph, which is the set of all ordered pairs x comma f of x, where x is an x, that obeys the vertical line test. And then we could use the graph of g to define the value f of x and y for each x and x. And again, he points us to exercise 3.5.10, which we'll get to in section 3.5, later on down the line. Right, or option 3, start with a mathematical universe U without any functions in it, and use definition 3.3.8 to create a larger extension of this universe that contains function objects and that behave as specified in definition 3.3.8. But he says option 3 requires a bit more of the formalism of logic and model theory than is provided by Tao's text, and so it won't be detailed here. Just a side note here. Let me just stop the screen share for a second. Model theory is an extension of set theory and logic that was developed by Alfred Tarski, and it is a subject that we'll eventually probably get around to on the channel. I don't know when, but I have this book by David Marker, which has some good reviews on it, Model Theory and Introduction. So at some point, I'd like to do an actual axiomatic set theory um, series on the channel, as well as a mathematical logic series on the channel, and maybe we'll after those two we'll get around to model theory. There's also a branch of logic and set theory called proof theory, which might be interesting at some point in the future to look at as well. But anyway, that's neither here nor there. We're not going to deal with that in Tao's book. Okay, next is the definition of composition of two functions, which is definition 3.3.13. Let f from x to y and g from y to z be two functions such that the codomain of f is the same set as the domain of G. We define the composition G, which is read G composed with F, from X to Z of the two functions G and F to be the function defined explicitly by the formula G composed with F of X equals G of F of X. So in other words, you evaluate F at the input X, and then you evaluate G at the output of F evaluated at X. Okay, just a note here, if the codomain of F does not match the domain of G, we leave the composition undefined. Exercise, excuse me, exercise 331 asks the reader to check that composition obeys the axiom of substitution. So again, that's something that we'll do when we get to the exercise set in the next video. All right, example 3.3.14, let f be a function from the natural numbers to the natural numbers, be the function f of n equals 2n, and let g be a function from the natural numbers to the natural numbers, be the function g of n equals n plus 3. Then g composed with f of n is g evaluated at the output of f evaluated at n, which is g evaluated at 2n, and just from the way that we define the rule for g, that's equal to 2n plus 3. Meanwhile, f composed with g of n equals f evaluated at g of n equals f of n plus 3, because g of n is n plus 3, equals 2 times n plus 3 by the definition of f. And then if you just simplify that using the distributive law, that's equal to 2n plus 6. All right, so just two examples of composition. But an important thing to notice here from this example, composition is not commutative. As you can see here, right? F composed with G is not necessarily G composed with F. So it's not a commutative operation. However, in the next lemma, we see that composition is in fact associative. So here's lemma 3.3.15. Right, let f from z to w, g from y to z, and h from x to y be functions. Then g composed with f, and then f composed with g composed with f is equal to f composed with g composed with f. Right, so associativity holds, in other words. And here's the proof. It's just using the definition, basically. G composed with h is a function from the set x to the set z, and that implies that f composed with the function g composed with h is a function from x to w, and f composed with g, if you from the definition, is a function from y to w, and that implies that the function f composed with g composed with the function h is a function from x to w. So notice that the domain and the codomain match, and then we just have to show that for each input value, the output values are the same for the two different functions. So if x is an element of the domain x, then if we look at first f composed with the function g composed with h evaluated at x, that means f evaluated at g composed with h of x, but g composed with h of x is the same thing as f composed with f evaluated at g evaluated at h of x. And that's the same thing as f composed with g evaluated at h of x, which is the same as the function f composed with g composed with the function h evaluated at x, just using the definition of composition. Therefore, the two functions are match at each element of the domains. Therefore, by definition 3.3.8, the two functions are equal. Therefore, composition is an associative operation. Right, another remark. There's a lot of remarks in this section, but they're good to note. So while we write G composed with F with G on the left, we actually apply F first. This is because we normally write F to the left of the input value when evaluating f of x. It's just a convention. There are some alternate notations. For example, if you've ever read Ian Herstein's book, Topics in Algebra, he uses the notation that the second notation that Tau specifies here, but it's not a popular notation. So he says there's some alternate notations that write the input to the left of f. For example, they write it as xf rather than f of x. This notation has not caught on as of yet. So like I said, there are some books that use that other notation, but it's not. I don't want to say it's not standard, but it isn't popular. You will see it in some books. Mainly I've seen it in like algebra, like abstract algebra books, but I haven't really seen it in other places. Maybe there are other places that use that notation. I don't know, but anyway, there is alternate notation, which makes the notion of the way that we write composition maybe seem a little bit more natural. But hopefully, if you've taken, like I said, like algebra or something, you're familiar to how composition works. All right, here's a definition. Definition 3.3.17. This is the definition of what we mean by a one-to-one function. Okay, we say a function is one-to-one. A function f is one-to-one or injective if different elements map to different elements. So, for example, if x is not x prime, that implies that f of x is not f of x prime. Similarly, you could write f of x equals f of x prime implies x equals x prime. This is what we mean by what we mean by one-to-one function. Sorry, I'm just looking at the volume. It looks like, I hope the volume is still working, because I don't see the levels changing. I'll keep going. Hopefully there's not a sound issue, but okay. Example 3.3.18. Again, he calls this informal because we haven't defined the integers yet. So the function f from n to z, n is the natural number, z is the set of integers, where f of n equals x squared is one-to-one, whereas g from the integers to the integers, where g of n equals n squared, is not one-to-one, since g of -1 equals 1, and that's the same value as g of 1. So two different inputs get mapped to the same output. This shows that the notion of a one-to-one function depends on its domain as well as on what it does. All right, remark 3.3.19, if f from x to y is not one-to-one, then one can find distinct x prime and x such that f of x equals f of x prime. Thus, one can find two inputs which map to the same output. Because of this, we say that f is 2-to-1 rather than 1-to-1. Just some terminology. Right, next important definition is 3.3.20. Here we're going to define what we mean by an onto function. A function f is onto, or sometimes it's called surjective, if every element in y comes from applying f to some element of x, or in other words, more compactly, for every y in y, there exists x and x such that f of x equals y, right? This terminology, injective and surjective, and what we'll see in a second, bijective, actually is vocabulary that comes from the Bourbaki school, the French school. But so you'll see it. It's pretty common, but there are other names that people use that I think are some people feel more comfortable with, like one-to-one or onto, or for bijection. Sometimes people say that the function is invertible, but just so you know the different terms, because they are used in different places. All right, here's another example, 3.3.21. Again, he calls this an informal example because we haven't defined the integers yet. So let f be a function from the integers to the integers defined by f of n equals n squared. That's not onto, since -1 is it's an integer, but is not f of n for any n and z. However, if a is defined to be the set of all squares of integers, then g from z to a is onto it. You get every element in a is g of n of some integer. Thus, the notion of an onto function depends not just on what the function does, but also on what its range is. Right, remark 3.3.22. The concept of injectivity and surjectivity are in many ways dual to each other. We talked about concepts being dual to each other in a previous section, but he says see exercises 332, 334, and 335. So we'll do those exercises when we get to the exercise set. Right, definition 3.3.23, bijective functions. A function f from x to y, which are both one-to-one and onto, are called bijections, or like I said, sometimes they're called invertible. Bijection is the Bourbaki term. Invertible is another way of saying bijection, but like I said, some people are more comfortable using one rather than the other, but just so you know what both of the standard terms are. All right, here's example 3.3.24. Let f be a function from the set containing 0, 1, 2 to the set 3, 4, be the function defined by these mappings. F of 0 gets mapped to 3, f of 1 gets mapped to 3, f of 2 gets mapped to 4. This function is not bijective because it's not 1-to-1, right? In other words, f of 0 equals f of 1, and 0 is not equal to 1. Right? Let G be the function from the set containing 0 and 1 to the set containing 2, 3, 4, be the function defined by G of 0 is mapped to 2, G of 1 is mapped to 3, then G is not bijective since G is not onto. In other words, 4 is not G of something in the domain. Right? And finally, let H be the function from the set containing 0, 1, 2, and to the set 3, 4, 5. Be the function defined by h of 0 is mapped to 3, h of 1 is mapped to 4, h of 2 mapped to 5, then h is bijective because it's both onto and it's 1-to-1. Okay, example 3.3.25. The function f from n, the natural numbers to the natural numbers minus 0, defined by the successor function, is a bijection. However, the function g from the natural numbers to the natural numbers defined by the successor function is not a bijection. Thus, the notion of a bijective function depends not just on what the function does, but also what its domain and codomain are. Right, just a few more remarks here, and I think we're done with the section. Right, remark 3.3.26. If a function x to f of x is bijective, we sometimes call it a perfect matching or a one-to-one correspondence, as opposed to a one-to-one function. We call it a one-to-one correspondence if it's bijective, and denote the action of f with the double arrow instead of the single arrow. Remark 3.3.27, do not confuse the definition of a function. This is essentially what he says in remark 3.3.27. I'm sort of summarizing here because it's kind of a long remark, but this is the point of it. Do not confuse the definition of a function with the definition of a bijective function, right? A bijective function is an example of a function, but not every function is bijective. Note that f from x to y, y equals f of x is a bijection, then the value of x for which y equals f of x is denoted by with this notation. This is read f inverse of y equals x. F inverse is a function from y to x, so you switch domains and ranges. We call f inverse the inverse of the function f. Okay, and I think that's the end of the chapter summary. Let me stop the screen share. Okay, so in the next video, like I said, I'll do the exercise set for section 3.3. That's going to take me a little while to do, like I said, because I'm in the middle of finals week and I'm just drowning in exams that I got to grade and so on. But hopefully sometime this week you can expect the video for for the exercise set from section 2.3. So thanks for watching, guys. Let me know what you think down in the comments. Please do like and subscribe. Take a look at the Patreon, all the YouTube stuff, and I'll see you in the next video. Until the time, everybody, keep learning.